In 1993, Diamond Computer Systems released their Viper VLB video card. You know what game arrived later that same year? Doom. Know what game the Viper VLB struggles to run? Doom. And other games that came after it. This card was meant to take advantage of the VESA local bus interface and its speeds to provide acceleration in Windows. This arrives courtesy of the Waytec Power 9000 graphics chip. With a chip focused on acceleration in Windows, the basic low-resolution needs of DOS were ignored. A decision was made to simply pair the P9000 with a second chip on the same card to handle those needs. In my card's case, that second chip was an Oak Technologies OTI 087X. This chip is not fast and is used to run most standard issue DOS games on the Viper, games that run at 320 by 200 resolution, for example. That would be a lot of them. If we look at this block diagram for the card, we can see that the companion chip is accessed through the slower, older ISA bus at around 8.25 MHz. Meanwhile, the P9000 is accessed via the newer, faster VESA local bus, and in my case, this is running at 33 MHz. Now there's a lot more to this, and I do not have the programming guide for the P9000, but the short story is slower and faster. Even if you never had this card back in the day, you may have heard of it before, courtesy of an LGR video that features it and is brought to you by his now famous Woodgrain 486 system. Benchmarks ensue, and the Superscape VGA benchmark helps tell the tale. After scoring 55.7 with his Cirrus Logic 5428 base card, the Viper dropped his score to 32.5. I'll let him summarize this drop in score with what seems like a rhetorical question.
That Oak VGA chip though, what are you gonna do?
And that question made me wonder, would it be possible to run low-res DOS games on the Waytec chip instead? As Jim Kirk once said, there's gotta be a way. And there is. The method requires a bit of madness, so let's zero in on the problem a bit more first. Flight Simulator 5 for DOS also arrived in 1993, and it provided a Super VGA mode option, 640 by 400 at 256 colors. But if we try to run it on the Viper, it doesn't work because the card isn't VBE 1.2 compatible. VBE 1.2 was a standardization for Super VGA modes that allowed software to say things like, hey, I need 640 by 400 at 256 colors, and the video card's BIOS would reply, sure, no problem, I have that mode right here. In our case, the Viper says, what? Maybe you just dropped $550 on this card in 1993. It is allegedly quite fast and can do all sorts of fancy Windows stuff, but it can't do 640 by 400 at 256 colors in the latest Flight Simulator, at least not without help. VBE 1.2 was defined in 1991, and video cards sold in 93 may have had the functionality built into their BIOS, while others had to use a TSR, a program you load into memory that sits there and handles VBE 1.2 functionality. So Diamond provided a VESA TSR utility for the card called VPR mode, and perhaps did so rather reluctantly. Even after setup gives you permission to run in Super VGA mode with this TSR in memory and you load up Flight Simulator 5, it has graphical glitches. This lackadaisical implementation led to a third-party utility called VPR VESA, a TSR that overcomes the pitfalls of Diamond's version. So if we use this TSR instead, Flight Simulator runs without a flashing box at the top of the instrument cluster. Excellent. While higher resolution and higher color modes are great, they're used by a rather small percentage of DOS games. The heavy hitters still make use of that lower resolution 320 by 200, and our needs return to that slow Oak chip. That's where a secondary utility from the makers of VPR VESA comes into play. Set Mode is our gateway to better performance. This utility lets you create custom video modes on your Viper VLB card and make use of the P9000 chip. All you have to know is how a CRT works. But rather than break down all of these signal components and timings, the short version is this. VGA was designed around output to a 31 kHz CRT monitor. The horizontal frequency is the number of times per second that the electron beam moves from the left side of the screen to the right and back again. Some quantity of horizontal scan lines make up a single frame, and then the beam returns to the top to start drawing the next frame. That vertical frequency, measured in hertz, is how often the image sent to the screen is refreshed. The timing you see here is for a 640 by 400 image refreshing at a rate of 70 Hz. This is more or less the same timing used by 320 by 200. But how. If the scan lines are firing at these speeds, how does 320x200 fit that timing? VGA cards use half the pixel clock speed, so the electron beam continues to draw the pixel across the screen for a longer period of time, as in twice as long. That's how 320 pixels fill a horizontal line at this 31 kHz line speed. VGA cards can also do double scanning. Each of the 200 lines of graphics is output twice, thus filling the 400 scan lines. So graphics that would only provide enough information to fill a quarter of the signal timing for output to the monitor are adapted to fill said timing. This is accomplished using specific VGA registers. These registers were essentially not implemented on the P9000. So for modes that need this sort of thing, and probably plenty else I'm leaving out, the Oak support chip is used. While it might be possible to tell the WATEC chip to do something similar, it is handled in a different manner. Perhaps we could reprogram some DOS games to take advantage of this, but this is outside the scope of this video. But what we can do is create a custom 320x200 mode and ultimately offer that mode to any software that requests it. We have to do so without any pixel stretching or scanline doubling. What we get is a 320x200 image framed inside 640x400 timing. And it works. If I load the VPR VESA TSR and tell it to activate our custom mode, we end up with a 320x200 low resolution VESA mode. PC Player Bench can see this mode and run it. We now have the ability to create a comparison of sorts between the Oak and the WATEC chip by using the same software. But obviously, the small image is a big problem. You'd want to stretch this image to be twice as wide and twice as tall. Now, I still have the manual to my first Super VGA monitor that I upgraded to around 1993, and it represents a feature we had at the time. And that feature is a series of analog knobs that let the user change the size of the width and the height of the raster on the screen. The fact these were analog knobs and not digital menu settings meant you could stretch or compress the image rather quickly, but the disadvantage was that this feature was not going to let you double both dimensions and size. It was a much smaller percentage of an adjustment. Fortunately, I have this hooked up to a modern scaler. This allows me to zoom the image to the appropriate size. Maybe it isn't very 1993-ish, but it works. Of course, that also means we have to switch back and forth between zoomed and not zoomed when we aren't using this custom mode, just like if we were using a period correct monitor. It's too bad there isn't a way to scale it before it is output from the computer. Wait a second. I followed VGA standards and used the fixed horizontal frequency of 31.5 kHz that was meant for VGA monitors at the time. Low resolution, no problem. Stretch the pixels and double the scan lines to accommodate VGA monitor timings. This is the way. Monitor is none the wiser. But along comes the WATEC P9000 that wasn't designed for this, so we scale output manually to fit these standard monitor timings. However, we have curated programmer access to VGA output, and therefore freedom with the video signal. And I'm not outputting directly to a VGA monitor. I'm outputting to a scaler and then a monitor. Why not just cut the line speed in half and target 15.7 kHz like an arcade machine or a video game console? We don't need 400 scan lines. We only need 200. This means we don't have to stretch the pixels horizontally by holding them for a longer period as they are output. They will just clock out at the slower frequency. This eliminates our VGA register needs. And what we get is a full screen 320x200 image thanks to our slower line speed. The scaler sees this as a completely different mode and processes it accordingly. No zooming is required. One thing to note though, 15.7 kHz horizontal is typically paired with 60 Hz vertical. These timings work well. Since DOS games use 320x200 at 70 Hz, I flexed the horizontal speed in order to achieve a vertical timing as close to 70 Hz as possible. I did this for compatibility with the software, as several games expect this timing. It is possible that we could get something closer to a more industry standard 15.7 kHz at 70 Hz refresh, maybe, or even drop our vertical refresh to a much more modern friendly 60 Hz output. By the way, I tried this and it worked. But 16.75 kHz is what I used to make this video, as I wanted DOS game compatibility and I have a scaler that doesn't care about a specific frequency. With this alternate 320x200 mode created, we can load it into memory using VPR VESA and be on our way. PC Player now loads and shows at the appropriate size without requiring any user intervention at the scaler. Note that you could do this back in the day with the software and pair it with a multi-scan monitor that supports 15 kHz. Probably. I don't have one of those to blow up. I mean to test. It would be interesting to try out, as native 15 kHz output would mean we would likely see DOS games with a scanline effect to them. Now there is one other thing that we need to do to make this truly worth it. We created a 320x200 low-res VESA mode. It's available for any software that supports it, such as this benchmark, or something much more entertaining, like Duke Nukem 3D. However, we could also write our own TSR to simply take a software request to use our standard mode 13 hex that is destined for the Oak chip and instead redirect it to use our custom mode. Now we can run software intended for mode 13 hex and get it to use the WATEC. And yeah, it makes a difference. The WATEC chip leaves the Oak benchmarks in the dust. Synthetic benchmarks can be useful, but let's establish a performance baseline and switch over to games. But first, to the hardware. The system I'm running right now is an Intel DX4 overdrive at 100 MHz with 16K of write-through L1 cache paired with a motherboard using the SYS471 chipset. In addition, we have 256K of write-back L2 cache with the alter bit in use, 24 MB of RAM, a later revision of the Diamond Viper VLB card with 2 MB of VRAM set to 0 wait states. Storage uses a caching controller, there's a sound card in here somewhere. BIOS memory and VLB timings are pretty tight. No expanded memory manager loaded, no mouse driver. There was the quick system summary. Okay, that said, it's game time. Let's start with Duke Nukem 3D Atomic version 1.5 running on the Oak chip at 320x200 mode 13 hex. Note that I dropped the sound settings fairly low. This may provide a gain in performance, but it isn't extraordinary. If we start a new game with the frame rate counter showing and wait for the ship to crash, we just barely kiss 20 FPS. Duke doesn't have a built-in benchmark, but the start a new game and just stand there benchmark is a pretty good one. For the Oak chip, we sit at 19 FPS. Detail is on high, the screen size is maxed but with the HUD still showing at the bottom, and tilting, which I believe relies on floating point, is turned off. Let's get the first demo to roll. It should look familiar to those of you that have watched the wood grain videos. I mean, it seems playable, he said to the viewers with a large question mark over his head. This is an example of how it would run on a mid-90s 486 with a Viper card. None of our TSR overrides are in use. Would this push you to drop goodness knows how much money to move to a Pentium machine in 1996, the same year this game came out? Maybe? Probably not though. That said, Quake hits a few months later and probably has you feeling kind of bad about your system. Think about this hardware paired with this game at the time of Duke's release in 1996 for a moment. You're looking at a system with a very expensive VLB graphics card purchased within the last 3 years as it first came out in 1993, as well as a fairly recent processor upgrade to a DX4 overdrive. Turns out your video card is bottlenecking your system much more than you think. We're averaging frame rates in the upper teens to mid-20s. The lowest I saw was close to 14 and it happened a few times. Overall, it is okay. I mean, high detail with a decently sized viewing window. You'd probably play it like this back in the day, maybe even tweak the window size a bit and feel like you'd want to hold out for a Pentium upgrade just a bit longer. Now let's load setup and switch over to VESA 320x200, ignore the warning about VBE 2.0 as we are running VBE 1.2, and launch Duke again. If we start the game, activate our frame counter and let the ship crash, the frame rate stabilizes at around 33 to 34 FPS. That is an insane performance boost. I know we're just standing here, but being north of 30 FPS is a pretty good sign. Remember that we were running sub 20, standing in the same place with the same settings when using the Oak. Performance will fluctuate with action, of course, so let's check out our demo sequence. This demo runs very well, to be honest. Duke 3D isn't quite the 486 killer that Quake would become, but if you're holding off on dumping the cash on a Pentium upgrade, this performance out of your Viper card may have helped you wait it out a bit longer without hesitation. Again, if you didn't mind using your monitor controls to try and size up the image, or were lucky enough to have a multi-sync monitor that could do 15 kHz, you could have pulled this off in the 90s. The huge caveat, of course, would be dialing in your custom video mode without blowing up your monitor. With the P9000 chip responsible for Duke 3D, the game can hold 30 FPS at times. It does dip into the mid-20s here or there, with the lowest being the low 20s at worst. Maximum frame rate I saw at one point was, believe it or not, close to 60 FPS. Duke Nukem 3D also offers a 320x400 mode option. We could use 640x400 timings to create this mode and then stretch it on the horizontal using the scaler. Standing still test is close to what we saw with the Oak chip in mode 13 hex. If you want to get a bit more resolution out of Duke Nukem 3D and don't mind the performance hit versus tweaked 320x200, it looks like 320x400 is a pretty good option. I'm only running an Overdrive DX4100 with L1 in right through mode, so moving up to some faster CPU options and or upping your FSB speed, should the card manage to handle it, may result in even better performance when paired with a Viper using this custom mode. Finally, there's a modern tweaked version of Duke called Duke Mark that is made for benchmarking the game. This provides additional numbers during gameplay and will give a summary of performance at the end of playback of one of its demo files. A different set of demos than with vanilla Duke Nukem 3D, by the way. So if you're interested in seeing some resulting numbers rather than a traditional observation of Duke Nukem 3D, here's how the modes stack up against each other for Duke Mark Demo 1. And with that, we've wrapped up Duke, perhaps one of the best ways to benchmark a 486 as you move beyond 66 MHz. Of course, remember that other build engine games, such as Shadow Warrior or Redneck Rampage, could also take advantage of this custom mode, but Duke was our guinea pig. Now, I'm sure you want to ask me about Doom. This is a thing. It would really be nice to not have to use the Oak chip here. Unfortunately, there's a problem. Doom uses Mode Y, a tweaked version of Mode 13 hex. While our TSR will substitute our custom 320x200 mode, it won't really tweak that mode. Doom will assume the VGA chip is happy to be in Mode Y, but it isn't. What we get, you're going to love this, is a video wall of Doom. No pun intended. Now I'm going to call it playable. I mean, the footage you see right now is me playing the game, but it's pretty bad. Although it could be worse, we could make it interlaced, but let's not do that. The Oak version completed everyone's favorite Demo 3, and I run mine with the status bar, and managed just over 20 FPS. The Waytech version provides a wonderful backdrop for a music video and completed Demo 3 with a frame rate of just over 40 FPS. At this point, I do not have extra Waytech-based video mode tweaks available in a separate TSR, so we're kinda stuck as far as Doom is concerned. Or at least, vanilla Doom. However, if we leave the 90s and arrive in the present day, we have Fast Doom. Fast Doom is just like Doom, but faster. It's a port for DOS with a goal to make the game as fast as possible for 386 and 486 PCs. Among the many features of this absolutely amazing project is the ability to run the game in different graphics modes, like say, CGA, EGA, text modes, all sorts of fun stuff. But we just want it to look like regular Doom. While Fast Doom does have Mode Y, it also has both Mode 13 Hex and VESA mode support. Since we technically switched applications, let's baseline the Oak chip once again. For Fast Doom running in Mode 13 Hex, the Oak chip manages to hit over 31 FPS. You can probably tell it is running faster than vanilla Doom. So you might ask, well, is our custom mode going to be faster? Oh, just wait. Despite the native 320x200 VESA support, let's activate our Mode 13 Hex TSR to substitute our custom mode for it and see how things go. Well, the answer is they go faster. If you thought the performance increase in Duke Nukem 3D was good, I mean, look at Doom. The demo completes and we managed to hit just under 60 FPS. The funny thing is, we are leaving performance on the table. There are two 320x200 VESA modes available. We have access to a back-buffered mode, which is considered more compatible than the additional direct mode that uses triple buffering. Both of them want VBE 2.0. We have VBE 1.2. Back-buffered mode does run, looks okay, and gives a score around but slightly less than the Mode 13 Hex override score. We can also run the direct mode on the Viper at the expense of some flashing. And well, that benchmark almost reaches 68 FPS. Now, technically, it isn't working properly, so I don't know if we should count this, but it is pretty fast. Benchmarking a game is cool, but running the game at normal targeted 35 FPS is better. If we enable the FPS counter in-game and let it run normally, the Oak chip maintains this demo at close to the intended 35 FPS at times, but still manages to dip into the upper 20s. To be honest, it's not too bad. Fast Doom's optimizations are really helping here. Of course, with the override TSR active, the P9000 has no problem maintaining 35 FPS, at least in this demo. Let's wrap up with a few other games. Both Heretic and Hexen use a modified Doom engine that runs in Mode 13 Hex instead of Mode Y. That's convenient for our override. While the benchmark method used in Doom is not available here, they do have a feature for performance tracking that is activated by typing ticker once the game is running. This one is interesting. You have these white pixels appear during gameplay to help give you an idea of what your frame rate is. Divide 35 by the number of dots to get your frame rate at that moment. So in an ideal situation, you will only see a single dot at all times and run at a steady 35 FPS, the intended frame rate for the game. If we run it on the Oak as well as the Waytech using the TSR override, we can compare the performance of the two at the same time. I've enlarged the dots for each version and also cropped out the first dot. Any white boxes that appear below therefore indicate a drop from the intended 35 FPS. The more white boxes there are, the more severe the drop in performance. Note that this footage of both versions isn't perfectly in sync as the game is timed to 70 Hz but the scaler is outputting 60 Hz. The aspect ratio is slightly different between the two, so the boxes and masks I created for them are not even. That said, the override to VESA TSR does make a difference. I did notice that the Waytech would sometimes slow down more than the Oak on frames when a screen flash occurs when taking damage. However, the Waytech P9000 seems to run things much better overall. The second demo sequence showcases the Waytech holding 35 FPS at the start. Meanwhile, the Oak chip has to lean on some frame drops in order to keep up. In the modern era, there's always a possibility that Heretic will be supported by Fast Doom at some point in the future, and that should make a huge difference for both chips, as you saw with Doom. I mentioned Hexen, and the same functionality exists for this game. So here is yet another popular title that could take advantage of this. Hexen hit in late 1995. This would be right in the wheelhouse of this system and be yet another title you would probably want to have already running well when Duke Nukem 3D arrived. Speaking of mid-90s computer killers, Descent brought us into 1995, and oh, does it require some system power. The source code was released a few years later, and I'm using a work-in-progress version that adds benchmarking. It can also provide a frame rate counter during gameplay or demo playback. If we set the game to highest detail and let the main demo run, our custom mode override seems to have an advantage just as we would expect. At the end of the demo, the game writes a benchmark file with some detailed information from the demo playback. While this engine could perhaps use some tweaks to provide better performance overall, the results show that the custom override mode does seem to increase performance. If you're someone that wants a period correct 486 DOS machine and also wants to select an appropriate VLB card to go with it, I would not recommend the Viper VLB. That said, if you have one already, or you just like to tinker with hardware as I do, there is perhaps more power at your fingertips than you think. There are many other DOS games to run aside from the ones I have shown, but I thought this group was a pretty good showcase of how well popular, performance-demanding games of the era could have run on a Viper VLB card. While there are perhaps more questions to be answered concerning what could have been with this card, I think this is where we will stop. And so I will say, happy DOSing, and thanks for watching.